Hello everyone, it's the Science Chef again. Today we'll be looking at the ideal gas equation, the fourth part of a series on the gas laws. Go nowhere, I will see you on the other side. If you'd like to watch more of these tutorials, please like this video, subscribe to our channel and turn on your notification bell. If you'd also like to watch our tutorials on the Boyle's law, Charles' law and the general gas equation, check the link in the description. The ideal gas equation is derived from the Boyle's law, Charles' law and Avogadro's law. We will learn more about Avogadro's law in our subsequent tutorials. A combination of these laws gives a joint variation among the four parameters: volume, pressure, temperature and number of moles. Introduction of a proportionality constant and rearrangement of the equation gives the ideal gas equation PV equals to nRT, where R is the molar gas constant and N is the number of moles. We can also say that the ideal gas equation shows a relationship between the pressure, volume, temperature and number of moles of a gas. Recall that number of moles N is given as mass over molar mass, and substituting the value of small m over big M for N in the ideal gas equation, we obtain an alternative form of the equation PV equals to small m RT over big M, which gives the relationship among the pressure, volume and temperature of a gas with its mass and molar mass. The values and units of R depend on the values and units of P and V. For 1 mole of a gas measured at standard temperature and pressure, when the pressure is 1.01 times 10 to the power 5 Newton per meter squared, volume is 0.0224 meters cubed and temperature is 273 Kelvin, the value of R will be 8.314 joules per Kelvin per mole. Alternatively, when the pressure is 1 atm, volume 22.4 dm cube and temperature 273 Kelvin, the value of R will be 0.082 atm dm cube per Kelvin per mole. Recall that 22.4 dm cube or 0.0224 meters cube is the volume occupied by 1 mole of any gas at STP, and it is called the molar gas volume. Let's now look at the applications of the ideal gas equation. Question 1. A given amount of gas occupies a volume of 5 dm cube at 3 atm and 30 degrees Celsius. Calculate the number of moles present. Take R to be 0.082 atm dm cube per Kelvin per mole. Solution. From question 1, we are given the pressure as 3 atm, volume as 5 dm cube, temperature as 30 degrees Celsius, which is equivalent to 303 Kelvin, and R, the molar gas constant, as 0.082 atm dm cube per Kelvin per mole, and we have to find the number of moles N. The question requires an ideal gas equation given that it involves pressure, volume, temperature and number of moles. So using PV equals to nRT, making N the subject of formula and then evaluating the equation, we obtain 0.604 moles as the number of moles of the gas. Question 2. 5 moles of an ideal gas are at a temperature of 260 Kelvin and a pressure of 2.02 times 10 raised to the power 5 Newton per meter squared. What volume in dm cube will the gas occupy at that temperature? Take R to be 8.314 joules per Kelvin per mole. Solution. In question 2, we are expected to calculate the volume occupied by the gas, and we are given the pressure, temperature and number of moles as 2.02 times 10 to the power 5 Newton per meter squared, 260 Kelvin and 5 moles respectively. Since R is given in joules per Kelvin per mole and the pressure is in Newton per meter squared, then our volume will be in meters cubed. So if you apply the ideal gas equation PV equals to nRT, make V the subject of formula and evaluate the equation, we will obtain 53.5 dm cube as the volume of the gas. Question 3. What mass of nitrogen will occupy a volume of 3500 cm cube at a temperature of 35 degrees Celsius and a pressure of 2.5 atm if the molar gas constant is 0.082 atm dm cube per Kelvin per mole? Take the relative atomic mass of nitrogen to be 14. Solution. In this question, we will be applying the second variant of the ideal gas equation that relates mass and molar mass of the gas with its pressure, volume and temperature. Also, given that the values of R and P are in atm dm cube per Kelvin per mole and atm respectively, then we must convert the volume to dm cube. From the parameters provided, Pressure is 2.5 atm, volume is 3500 cm3, which is equivalent to 3.5 dm3, temperature is 35 degrees Celsius, which is equivalent to 308 Kelvin, and molar mass of nitrogen is 28 grams per mole, since it is a diatomic molecule. So using the ideal gas equation, PV equals to small m RT over big M, making small m the subject of formula and evaluating the equation, we obtain 9.701 grams as the mass of the gas. Question 4. At what pressure would 2.0 moles of a certain gas occupy a volume of 44,800 cm3 at 273 Kelvin? Take R to be 8.314 joules per Kelvin per mole. Solution. Here, since the value of R is in joules per Kelvin per mole and we are to find P, our volume must be in meters cubed. So, from the given parameters, volume is 44,800 cm3, which is equivalent to 0.0448 meters cubed. Temperature and number of moles are 273 Kelvin and 2 moles respectively. So given a PV-Tn relationship, we'll make use of the ideal gas equation, PV equals to nRT. Make P the subject of formula and evaluate the equation to obtain 1.013 times 10 to the power 5 Newton per meter squared as the pressure of the gas. Do you observe that the pressure we just calculated is the standard pressure? This makes sense because the volume of 44,800 cm3 or 44.8 dm3 is the volume that will be occupied by 2 moles of a gas at STP, given that 273 Kelvin is the standard temperature. In our next tutorial, we'll be learning about the Dalton's law of partial pressure. Till then, stay safe.